So if I've got, let's say, a box or a razor on a surface, and I'm applying a force onto the box, and I now see what happens. So we said initially, if I apply the force, there's an equal but opposite force opposing it. So because of friction between the box and the surface, there is a force that is directly opposite the force that I'm applying, but it's being applied on the box. And that force we call friction. Now if I increase my applied force, I'm not necessarily getting this box to move. Yet if I increase this towards some sort of threshold, suddenly the box does start to move. So a nice way that I'd like to visualize this is if we think about if let's say on this axis we draw the magnitude of the force that we're applying in newtons, and on this axis we plot friction. So initially, if let's say I apply a small force, I get exactly the same force back, right? So I get no motion. So I'd apply, let's give this numbers. Let's say this was 1 Newton, and I get 1 Newton of friction back. So I get no motion. Now I double the force. So let's say I now apply a force of 2 Newton, and let's say the box still doesn't move. And that means the force of friction opposing it has to be equals to 2 Newton as well, because then the sum of forces on this box will be 0. So still no motion. Now I increase the force, so we could already see while the box is not moving, whatever the forces I'm applying is equals to the force of friction. So there's this nice linear relationship. Now all of a sudden, over here, at some threshold force, let's call it F max, I get that the box does move, right? So if I just push hard enough, all of a sudden I get motion, which means at this point, very suddenly, the force of friction must be less than the force that I'm applying, because that's the only way this box can get into motion. So at some critical point, suddenly the force of friction now is something less, and it doesn't now, to a good approximation, if I push harder and harder and harder, the force of friction doesn't change. So it means if I were to try to find a relationship between the force that I'm applying and the force of friction, it has to look like this. Because the force that I'm applying is the one that's increasing, so it becomes larger and larger and larger, and it is matched by the force of friction up to a point, and then the box is moving. So just the axes were swapped around. So over here, we say the box is not moving. And over here, we've got that the box is moving. And we're going to use this to define two types of friction. When the box is not moving, we will be talking about static friction. And when the box is moving, we will talk about kinetic friction. Now, if you've ever tried to move something, what would you rather do? Let's say someone asks you to just push a box full of papers from one point in a room to another. If your friend sits on the box, would that make it easier or more difficult? More difficult. So somehow if I increase the mass, so let's say I put another weight on top of the box, so I'm increasing the overall weight of this whole object that needs to be pushed. Somehow I must now push harder to get it moving in this direction. So if I've increased the weight, remember the normal force is always the one that counteracts this. So I've increased effectively also the normal force from the surface on the box. So we can basically say that the larger the normal force is from the surface, the larger the force of friction will be. So to a very rough estimate, to first order, we can say, well, this force of friction has to be proportional to the normal force. Because if I put another mass on top of this box, the normal force from the surface has to be larger, and I find it's more difficult to push the box in a certain direction, which means the force of friction had to be larger. So if I increase the normal force, I generally increase the friction. And for when we've got a moving object, we can say, well, the force of friction is equals to a number. It's got no units. We just call it Greek letter mu k times the normal force. And note, this is in terms of magnitude. So this is not a vector equation. This is the magnitude of the force of friction related to the magnitude of the normal force. And this is called the coefficient of kinetic friction. For static friction, it's slightly more difficult. The only thing we can do is we know right at this threshold, we've got that whatever the force of static friction was, it's overcome right over there. So we can say, well, the maximum force of static friction is related, so that force is related to a different coefficient, which we call the coefficient of static friction, times the normal force. And these coefficients are material dependent. So for example, ice will generally have a smaller coefficient of friction associated with it than, for example, sandpaper. So this is something that you usually have to determine either from experiment on your material, but it does give us a nice way to relate the normal force to a force of friction. And as you'll see next week, we will apply this in a few situations. And there's actually an experiment that you can devise where you can calculate both these coefficients for a specific material. That's quite simple. And you'll also see, by the way, this does not depend on any property of the object that's sliding on the surface. Thank you.